Okay, so we had a little technical glitch. Let me just refresh our memory where we're at with this problem here. This is a 5th degree polynomial. So we know that it has to have a total of 5 roots, including complex roots, repeated roots, and whatnot. And so we're trying to figure out how many distinct real roots this thing has. Sounds like a location of roots problem. And so far the group here has managed to figure out a few things. We plugged in some values here. The f of 10 was because we knew this function blows up as x gets really big. We can get definitely a positive value there. But we have some alternating positive and negative values that allowed us to produce 2 real roots, for sure. Okay? The complex roots have to come in pairs, so I can't have just 2 real roots, because if I had 2 real roots, that would mean 3 complex roots out of a total of 5 roots. You can't have 3 complex roots. By the way, this is a fact that's beyond the scope of what we covered in the class, so I would just be giving you this as a hint. But anyway, once you have 2 real roots, you better have at least 3. Okay? You have to have at least 3. So the question is, are there 3 real roots or are there more than 3? Well, you cannot have, again, you cannot have 4 real roots because then you'd have just a single complex root, and that violates this hint again. So it's either going to be, what are the choices for how many real roots we have? At this point, 3 or 5. Originally it was either 1, 3, or 5. Right? You either have 1 real root, 3 real roots, or 5 real roots, but you already found 2 real roots, so you can't have 1. You've got either 3 or 5. Okay? So, question is, which one is it? Now, suppose there are 5. Okay, I think this is what Jenna was getting at here. Suppose there are 5 roots, guys. Here they are. The function comes through here, goes there, goes there, goes there, goes there. Right? Suppose there are 5 real roots. So what is wrong with that?
There's 4 points where the derivative is 0.
Right. If this was true, there would be 4 different points where the derivative is 0. These are 4 different points, mind you. 4 different points. Now, when you look at the derivative, you might say, well, this does have 4 roots. But notice it was rigged so that the roots, we actually know these roots, 0, -3, and 2. These are the only distinct roots. Right? So there's only 3 distinct places where the derivative is 0, so you can't have 5 real roots, right? That's the point. So you can't have 5 real roots because of this idea. You can't have 4 real roots or 2 real roots because it would give you an odd number of non-real roots, which violates my hint. And we've shown that there's more than 1 real root. So out of all the numbers, the only one left is that there's 3 distinct real roots. That is the answer. That is the answer. Does that make sense? This is a nice application of the intermediate value theorem. Be sure that, so the intermediate value theorem requires your function to be continuous on the closed interval. If you're hoping to use the mean value theorem, make sure that your function is given to you as something differentiable. Now this is differentiable anywhere. There were some people on the midterm recently that were trying to use the mean value theorem on a problem where I didn't give you a differentiable function. You don't want to do that. Okay, make sure that you can actually apply it before you do that. Okay, so I'm going to be a little choosy here about what other things I want to go over. Are there any particular areas you guys want more practice on, or just you're happy with my selection so far? Okay. Let's try and do a few more. I may not get through all of these because I need to stop at some point. Take a bit of a break. We'll go through a little bit more here. Might end up closer to 3 hours than 2, but that's not surprising for a final review. Okay, so am I on number 7? 8. 8. Number 8. Okay, number 8. Okay, so let f differentiable and 0 less than a less than b. Now let's just say f is differentiable on the closed interval ab. We'll just use that. So suppose that f is differentiable on the closed interval ab. Prove that there exists a c in the real numbers such that f prime of c is equal to the square root of b times f of b minus the square root of a times f of a all over the square root of c times the quantity b minus a, and then minus f of c over 2c. What's that?
This one again.
Have I done this before?
It's
It's a similar one on the exam.
Vector tangent.
It's similar to the one on the exam. Okay, so do you guys know how to do it?
Yeah.
Okay, how do you do it?
G equals x. Yeah, we can.
Define, what's that? G of x.
Is x times f of x.
No.
Or square root of x.
Square root of x times f of x. There you go. G of x is equal to that function. Okay, and you use the fact that you can apply the mean value. So maybe I won't go through this one. You apply the mean value theorem to this function, right, on this interval AB. And you have to use the product rule to figure out g prime of c. The mean value theorem applied to g gives you a c such that g prime of c is equal to g of b minus g of a over b minus a. Okay, so you guys are good on this one.
Yeah.
Okay, then let's not spend time on it. I want to focus on the things that would be more useful. Okay, so we're just going to not even solve that one. That was number 8. We'll just write problems on the board and not solve them. Okay, let's try another one. Oh, you want to do that on the test? Okay, here is another one. So number 9. Okay, I actually mentioned this in class on Wednesday, but then I didn't actually prove it, so this would be good to practice. Prove if f is Riemann integrable, then the absolute value of f is Riemann integrable. This was one of those parts of Corollary 6.1 that I didn't really write the proof out for. So I thought we might do that here. Okay? What do you want to start me off with?
Since f is Riemann integrable, we can use theorem 6.2 to get the stuff.
Great, it's theorem 6.2, right? Proving Riemann integrability is almost always theorem 6.2. Very good. So what's the first line of the proof?
Epsilon be greater than 0 be given.
All right, let epsilon greater than 0 be given. Always start that way. Okay? Now f is Riemann integrable, so now Anthony wants me to use theorem 6.2. By theorem 6.2, there exists what? A partition. Okay, I didn't give you an interval here, so don't worry about it. Okay, there exists a partition, and what is the requirement now? U of PF minus L of PF is less than epsilon. Very good. So this is the condition. Yeah. Okay, so that's true for the function f. And we sort of want to get the same thing for the function absolute value f. Is there another way to write the UPF minus LPF? Not with absolute value bars, just using the definitions of the U and the L. It's the summation of what now?
Capital
M I delta xi.
Okay, what I'm going to do is I'm going to factor the delta xi out, right? So I can factor out the delta xi, and I'm just subtracting the big mi's and the little mi's. And what I could do here is I could emphasize that this is big mi's and little mi's for f. For f, right? So you're taking the supremum and infimum values of the original function little f on the subinterval corresponding to xi, delta xi.
Can you take the absolute value thing, and then we can use the triangle inequality to say that it's mobile?
Okay, basically, as soon as you replace f with the absolute value of f, the difference between the supremum and infimum can only get smaller, right? Can only get smaller because your function f might be like this. Your big mi is way up here, and your little mi is down here. As soon as you take the absolute value, your little mi gets closer to the big mi, right? So that's the point. So this expression here, we know that it's less than epsilon. So now, since I'm just going to emphasize the main point here, the big mi for the absolute value of f minus the little mi for the absolute value of f, that is always less than or equal to the big mi for f minus the little mi for f. That's just always true. So u of p absolute f minus L of p absolute f, right? This is going to be the summation I going from 1 to n of big Mi for absolute value f minus little mi for absolute value of f delta xi, which is less than or equal to the same summation for the big mi's and little mi's for f, and that just gives times delta xi, and that just gives you UPF minus LPF, which is given to be less than epsilon. So you just build that chain. Pretty good? Okay, so that is a nice little, pretty easy proof. Yeah, Eric?
Could we also try arguing about constructing other Riemann integral functions with another continuous function, like we talked about on the last day?
What are you asking? You're asking me to make another problem?
Well, no. Could we?
Oh, you're talking about how to do this.
Yeah, can we show that this is Riemann integrable by introducing like a function, continuous function that takes it to absolute value?
Absolute value of x and f, right?
Yes, but we didn't prove that compositions of Riemann integrable functions are Riemann integrable, right? We know that continuous functions are Riemann integrable, and so if you're putting together continuous functions, you could do that. I mean, I think what you might be getting at, Eric, is you could do something like this. You could say, well, suppose this is your function, right, and your interval goes from here to here or whatever. Right, what you might be thinking is, well, find a root, chop it there, and then say, all right, on this domain, f and absolute f are the same. So if f is Riemann integrable on the whole domain, remember we did prove that it's then integrable on any subinterval. So you could say, well, f is Riemann integrable here, therefore so is absolute f because it's the same function. Then you could go into this section, right, and just say, okay, on this section, now absolute f is just negative f. And you can say, all right, we know that if f is Riemann integrable, then so is any scalar multiple of f. So then this is Riemann integrable from C to D. And then go back up to this part and use that. I don't know if that's what you had in mind, but that's a good way that you could argue it. Of course, the way I drew it here, it's already continuous. But if it had lots of jumps and leaps in it, you could definitely do that. Yeah. That's definitely another idea. Okay, I have a little follow-up question here to this. We know that the absolute value of a Riemann integrable function is Riemann integrable. So then, can we prove this about it? So this is just a follow-up, a second little part here. Follow-up, show that if you do take the integral of f, right, that it's less than or equal to the integral of absolute f, and even if you take the absolute value of the left side. Okay, so if I had had 10 more minutes on Wednesday, I probably would have done this little problem, but I didn't have time, so I'll do it now. It's a great thing about the review session. I can just throw in some more problems. Okay. So, anybody have a thought about that at all?
So since we know that the f is integrable, right?
Yeah, but we're still assuming, I mean, if f wasn't integrable, I couldn't even write this down. Okay, remember guys, don't ever write this notation down unless you know your function is Riemann integrable. Okay, this sort of assumes that, yeah, okay.
So that means that on the left-hand side is equal to the upper sum?
This one?
Right.
Without the absolute value bars.
Right,
So this integral is equal to the infimum of all of the upper sums, or equivalently, the supremum of all of the lower sums. That's true. Okay. But too complicated, I think. Yes?
Can we subtract them both and show they're less than epsilon?
Subtract the two integrals?
Yeah, and show they're less than epsilon or something.
Well, do you think that's true?
Or,
Do you think that's true? So,
oh, wait.
let me give you an example. What if I give you this? Here's f right here. It's Riemann integrable, right? Because it's basically monotone or whatever. So it's Riemann integrable, but the integral of it is 0.
Yeah.
So that's 0. But then on this side of the equation, if you make it all positive, now you've got something that's b minus a times whatever the height is, and that, so that when you subtract them, with that example, you won't get that it can be less than epsilon. So it's a good idea, but this is a kind of a counterexample to that approach. This is actually a quick one to show. Do we have any results that involve comparing one integral to another? Have we done anything like this?
If f of x less than or equal to g of x, then the integration of f of x less than or equal to the integration of g of x.
That's it. I'm just looking up the number of the proposition. Very good, Sarah. It's basically, yes, it's proposition 6.4. If f is less than or equal to g, then the integral of f is less than or equal to the integral of g. So, what function will be less than what function here?
So the absolute
F is less than or equal to absolute value of f. Okay, great. So the integral of this one is less than or equal to the integral of this one. Okay, now that's not quite what we have here. So is there something else we need to...
Okay.
So if I have absolute value of z is less than or equal to 3, what does this mean?
It's either negative, c is less than or equal to 3, or
greater than negative 3 and less than positive 3.
Okay, so we actually, if this is what we're proving, right, I can actually put,
Negative absolute value of f.
right, I can put so this is like playing the role of the 3, right, in this little thing. So I can put the negative and the positive and sandwich this one between it, right? Right? Now if I just put integral signs in front of all of them, using proposition 6.4, we're going to have that. Agreed?
Yes.
What can you do with this minus?
We can take it out.
Put it outside. Now you have again, like you have the negative 3, less than or equal to something, less than or equal to 3. Which means that the absolute value of the thing in the middle, which is this, is less than or equal to this one. It's really that, it's just that simple. You're just using this little relationship right here to get that. Isn't that nice? I probably, with this one, I might give you a hint if I ask this, because it is a little different than the problems we've shown before. If I didn't have the absolute value bars on this, then it's like trivial, right? But then, when I do put the absolute value bars on it, you have to realize I'm not really making it more complicated. I'm just creating two inequalities out of it, but it's still the same proposition that you're taking advantage of. Yeah, so that, I just wanted to go through that. Okay, did that one. There's so many things to review. I don't even have, we've got Taylor's theorem, we've got, gosh, all kinds of things. Let's, let me think running out of time here, but I'm actually getting pretty good along on some of these. Okay, let's do a few more things. Okay, so number 10. Okay, find a set with exactly 2 accumulation points. Guys, remember these problems?
Yeah.
Yeah. 1 over n for n is a natural number.
Okay, so the thing about it is when you create whenever you have a convergent sequence, a convergent sequence always has exactly 1 accumulation point, which is the limit of that sequence. Okay, so here you go. What's the accumulation point for this?
0.
0. Okay, so that has 1. So then what are you going to do to get another one?
Union 1 over n plus 2 or 1, whatever.
Whatever you want, right? Just add something to it, right? Where n is in the natural numbers. Great. This has a single accumulation point, which would be 2. And then what do you do with these? Take the union, exactly. Okay, might be worth remembering the definition of an accumulation point. So let's just do that really quick, because we're writing this down because we remember the problem, but you have to remember why all these things are true. So let's just say x, which is some real number, is an accumulation point of A if, so do you remember what it is? For all neighborhoods, I'm going to refer to that as deltas. For all deltas greater than 0, and those are neighborhoods of x, by the way, right? So every neighborhood of x, so you're really going to be talking about x and then x minus delta to x plus delta, right?
Yeah.
So each of these neighborhoods has to do what?
There exists an element of x, not x excluding, or a excluding x.
There has to be an element of a in here, right? Other than x, because x might be in a as well. So for all delta greater than 0, x minus delta to x plus delta. If we look at that interval, right, it has to have a non-empty intersection with a minus x itself. So you have to throw x away, look at the rest of capital A, and see if it has any intersection with this interval. That's the idea. That's the idea. Is that good, guys? Make sense? Yeah? Okay, so that is the definition of an accumulation point. Okay, so for example here, 0 is an accumulation point. Every neighborhood of 0 contains terms of this sequence, which of course are not 0. The accumulation point doesn't have to belong to the set. Often doesn't. Yeah. Okay. So just go back and review some basic examples. The accumulation points of an open interval. Turns out it's the closed interval, right? Accumulation points of Q, right? Everything, every real number, right, would be an accumulation point of Q. So you've got some examples that you can go back and study. Okay, let's do another problem. Guys doing okay so far? All right. What better way to spend a Friday night? Nobody's going to be partying anytime soon, right? Okay, number 11. Hey, but this is fun stuff. This is fun too. Okay, so here's what I want to do. Suppose that xn converges to x, and x is a positive real number. So x is in the positive real number set. And suppose that Zn converges to minus infinity. Okay? Then I want to prove that xn times Zn, if I take this product of these two sequences, that converges to minus infinity. Okay, so I'm using a negative infinity on this one. Practice with negative infinity. Let's see if we can get anything out of this. I think it'd be good to, probably if it's on a test, I'm going to have a part A. Part A is going to say, what does it mean for a sequence to converge to minus infinity? Or I might even just do the, what does it mean for xn to converge to x? Let's just write them both down, okay? So xn converges to x. This is just the definitions. So the definition of xn converges to x. Can somebody tell me what it is? For all epsilon greater than 0. Existent and not. Very good. Perfect. Such that n is greater than or equal to n naught. Okay, great. Exactly. And actually, xn minus x can be less than whatever we want to put there. So we'll have to see when we get a little further along. And then Zn converges to minus infinity. I think this was not covered heavily in lecture, but it was at least in the group work. Yeah. So what would this look like? Remember, we're converging to minus infinity.
For all n less than 0, there exists.
For all what?
N less than 0, there exists.
Let's use a Greek letter because we're using the epsilon here. I'd rather make it look similar. Either an alpha or a beta would be a good choice. If you remember, I think we actually used beta. For all beta less than 0, for all negative betas, not a delta. We're talking about sequences here.
I think it's alpha.
It's just an n naught again, right? You're just trying to go far enough down the sequence such that something is true, right? So it's the same n naught, so such that we just need to review this. Okay, such that if n is greater than or equal to n naught, there's no f here, guys. There's no function.
Then xn less than beta. Is it greater?
Which, well, think about it. You're going to minus infinity. Less than beta. Okay, glad we reviewed that. Okay, that's the definition, right? So if we take any negative number beyond the n naught term, the sequence is below that negative number. Okay, does that look good? So we have these two. Assumptions, and now we're going to look at this guy. Okay. First of all, does it seem reasonable? Yeah. Should be true, right? Makes sense. Okay. Because you've got a positive x here. If this x had been negative, then of course we would expect a plus infinity here. Okay. But since this is a positive x and a negative infinity, we expect a minus infinity. Okay. So we know that we're proving. I always like to look at what is it we're proving. We're proving convergence to minus infinity, which means we need to look down here. Right? So let's let beta less than 0 be given. Sounds a little funny to say that. Let beta less than 0 be given. That's what we're looking at here, right? And our job is to hopefully come up with an n naught such that xn times zn will be less than beta. Okay. So we've got two assumptions here, and we're going to need to work with both of those.
Do we want to use the max of both of those?
Right. Once we find the two n naughts that we need, we're probably going to choose the maximum of those two. So whenever you're dealing with those deltas, you always go to the minimum delta. But when you're doing the n naughts,